Here's how to properly size the equipment grounding conductor, or EGC, for power factor correction, or PFC capacitors installed on a motor circuit. Firstly, determine the line-to-line voltage. This information can be found on the motor nameplate or measured using a voltmeter. For a three-phase system, the line-to-line voltage is often 480 volts. Secondly, calculate the total per phase capacitive current. The formula for capacitive current, or IC, is kiloVars times 1000 divided by the line-to-line voltage. In this specific example, we have two 35 kiloVar capacitors in parallel. Therefore, IC equals 2 times 35 kilovars times 1000 divided by 480 volts, which equals 145.83 amps per phase. Thirdly, determine the maximum fault current. The maximum fault current, or F, is typically 5 times the total capacitive current. Therefore, F equals 5 times 145.83 amps, which equals 729.17 amps. Fourthly, size the equipment grounding conductor. The EGC must have a minimum ampacity of 80% of the maximum fault current. Therefore, the EGC ampacity equals 0.8 times F, which means the EGC ampacity equals 0.8 times 729.17 amps, resulting in an EGC ampacity of 583.34 amps. Fifthly, select the proper wire size. Refer to Table 310.16 in the National Electrical Code, or NEC, to select the wire size with an ampacity equal to or greater than 583.34 amps. For copper conductors, a 750 kcmil wire has an ampacity of 585 amps or higher, thus satisfying the requirement. There are additional considerations to keep in mind. The EGC should be insulated or covered to prevent accidental contact with other conductors. The EGC should be routed with the circuit conductors and connected to the equipment grounding terminal of the motor. Follow all applicable NEC requirements for equipment grounding. In summary, for two 35 kV PFC capacitors paralleled on a 480 volts motor circuit, the equipment grounding conductor should be sized with an ampacity of 583.34 amps. A 750 kcmil copper wire or larger is suitable based on NEC Table 310.16. Always consult the latest edition of the NEC and local electrical codes for specific requirements and regulations in your area. Proper grounding is crucial for safety and equipment protection. Ensure all connections are made securely and tested for continuity. If unsure, consult with a qualified electrician. When calculating the capacitive current, ensure that the kiloVar rating used is the total kiloVar for each phase. If multiple capacitors are connected in parallel per phase, sum their individual kiloVar ratings. Using the correct line-to-line voltage is essential for accurate calculations. For three-phase systems, this is the voltage between any two-phase conductors. The fault current multiplier of 5 is a typical value, but it is important to verify this value based on the specific system characteristics and capacitor impedance. Higher fault current multipliers may be necessary in some situations. When selecting the equipment grounding conductor size, always choose a conductor with an ampacity equal to or greater than the calculated minimum. It is often advisable to select a larger conductor size to provide additional safety margin and accommodate future load increases. The NEC Table 310.16 provides ampacities for various conductor types and insulation ratings. Select the appropriate conductor type and insulation rating based on the operating temperature and environmental conditions. Remember to consider any directing factors that may apply, such as ambient temperature correction or adjustment factors for multiple conductors in a raceway. These directing factors can reduce the allowable ampacity of the conductor. The equipment grounding conductor should be installed in accordance with NEC Article 250, which provides detailed requirements for grounding and bonding. Ensure that the EGC is properly connected to the equipment grounding bus in the panel board and to the motor frame. Proper grounding helps to minimize the risk of electric shock and provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective devices to operate quickly and clear the fault. In addition to sizing the EGC, it is also important to ensure that all other grounding and bonding connections in the system are properly made. This includes bonding the motor frame, metal enclosures, and raceways to the grounding system. Proper bonding helps to create an equipotential plane, reducing the potential for voltage differences between conductive surfaces and minimizing the risk of electric shock. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Check for loose connections, corrosion, and damage to conductors. Test the grounding impedance to verify that it is within acceptable limits. If any problems are found, take corrective action immediately. Always de-energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow safe work practices to prevent electrical accidents. If you are not qualified to work on electrical equipment, hire a licensed electrician. Working with electricity can be dangerous, and it is important to take the necessary precautions to protect yourself and others. Furthermore, consider the impact of power factor correction capacitors on the overall system harmonic content. Capacitors can sometimes exacerbate harmonic problems, especially if the system already has significant harmonic distortion. In some cases, it may be necessary to install harmonic filters to mitigate the effects of harmonics. A power quality analysis can help to identify potential harmonic problems and determine the appropriate mitigation strategies. Also, ensure that the capacitors are properly protected against overcurrent. Install fuses or circuit breakers in the capacitor circuit to protect against short circuits and overloads. The overcurrent protection devices should be sized appropriately for the capacitor current rating. Moreover, check the capacitor voltage rating to ensure that it is suitable for the system voltage. The capacitor voltage rating should be at least 110% of the nominal system voltage to provide a margin of safety. Consider the operating temperature range of the capacitors. Capacitors have a maximum operating temperature, and exceeding this temperature can shorten their lifespan. If the capacitors are installed in a hot environment, it may be necessary to provide cooling to prevent overheating. Also, remember that the EGC is intended to carry fault current, not normal operating current. The neutral conductor, if present, carries the unbalanced load current. The EGC and neutral conductor should be kept separate except at the service entrance or separately derived system. Improperly connecting the EGC and neutral conductor can create a parallel path for neutral current, which can lead to overheating and other problems. Additionally, the size of the EGC is based on the size of the circuit conductors. However, in some cases, the EGC may need to be larger than required by the circuit conductor size. This can occur when the EGC is serving multiple circuits or when the fault current is very high. Consult the NEC for specific requirements. Also, note that the use of aluminum conductors for the EGC may require a larger conductor size than copper conductors. Aluminum conductors have a lower conductivity than copper conductors, so a larger size is needed to provide the same ampacity. Check the NEC for the appropriate conductor size. When installing the EGC, make sure that all connections are tight and secure. Use appropriate connectors and terminals. Loose connections can create resistance, which can impede the flow of fault current and reduce the effectiveness of the grounding system. Regularly inspect the connections to ensure that they remain tight. Consider using torque wrenches to tighten the connections to the manufacturer's specifications. This helps to ensure that the connections are properly tightened and prevents over-tightening, which can damage the connectors. Also, be aware of the different types of grounding electrodes that are available. Grounding electrodes can be rods, pipes, plates, or other approved devices. The type of grounding electrode that is used depends on the soil conditions and local requirements. Consult the NEC for specific requirements. When installing grounding electrodes, make sure that they are installed properly. The electrode should be driven into the ground to a sufficient depth to ensure good contact with the soil. The connections between the electrodes and the grounding conductor should be made with approved connectors. Test the grounding resistance to verify that it is within acceptable limits. In addition to grounding the electrical system, it is also important to ground any metal equipment that is connected to the system. This includes motor frames, enclosures, and raceways. Grounding metal equipment helps to prevent electric shock and provides a low impedance path for fault current to flow back to the source. When grounding metal equipment, make sure that the grounding conductor is properly sized and connected. Use approved connectors and terminals. Regularly inspect the connections to ensure that they remain tight. Moreover, power factor correction capacitors can improve the efficiency of the electrical system by reducing the amount of reactive power that is drawn from the utility. This can result in lower energy bills and improved system performance. However, it is important to properly size and install the capacitors to avoid problems. Oversized capacitors can lead to overvoltage conditions, while undersized capacitors may not provide sufficient power factor correction. A power factor study can help to determine the optimal capacitor size. Also, be aware that power factor correction capacitors can affect the operation of other equipment in the system. For example, capacitors can increase the voltage on the system, which can affect the performance of voltage-sensitive equipment. It is important to consider the impact of capacitors on the entire system when making decisions about power factor correction. In addition, the location of the capacitors can affect their performance. Capacitors should be located as close as possible to the load that is being corrected. This minimizes the amount of reactive power that flows through the system and reduces voltage drop. However, it is important to consider the environmental conditions when choosing a location for the capacitors. Capacitors should be protected from moisture, dust, and extreme temperatures. If the capacitors are installed outdoors, they should be enclosed in a weatherproof enclosure. Consider using automatic power factor correction equipment. Automatic power factor correction equipment uses controllers to monitor the power factor and automatically switch capacitors in and out of the circuit as needed to maintain the desired power factor. This helps to optimize the system performance and reduce energy costs. Automatic power factor correction equipment can be more expensive than fixed capacitors, but it can provide significant benefits in terms of energy savings and system performance. It's crucial to stay updated with the latest revisions of the National Electrical Code, as grounding and bonding requirements can change over time. Regular professional training and continuing education are beneficial for staying informed about best practices and code updates. Never compromise on safety when dealing with electrical installations. If there is any doubt about the proper procedures or code requirements, consult with a qualified electrical engineer or licensed electrician. Incorrect installations can lead to hazardous situations, including electrical shocks, fires, and equipment damage. Always prioritize safety and compliance with applicable codes and standards. Finally, proper documentation of the entire installation process is essential. Keep records of all calculations, conductor sizes, grounding electrode types, and connection details. This documentation will be helpful for future maintenance, troubleshooting, and inspections. It also provides a valuable reference for understanding the system design and ensuring its continued safe and reliable operation. Consider labeling all components and conductors clearly for easy identification. This can save time and effort during maintenance and troubleshooting activities. Use durable labels that can withstand the environmental conditions. By following these guidelines and taking the necessary precautions, you can properly size and install equipment grounding conductors for power factor correction capacitors on motor circuits, ensuring safety, compliance, and optimal system performance. Remember to consult with qualified professionals when needed and always prioritize safety in all electrical work.